The main purpose of this and the rest of the subsequent discussions is to just do a warm-up of our vector math before we dive into Maxwell's equations with vector math under our belts. So the purpose of this particular skill that we're going to talk about is I want you to be able to differentiate between a vector, scalar, a vector field, and a scalar field. So I want you to know what the key differences between them and how the notation, as well as when you see that notation, what it means. So let's start with a vector. So the two components of a vector are that it has both a magnitude and a direction. So if it's missing either of these, it's not a vector. And you indicate this by taking the difference from between the coordinate or a coordinate location and to the origin. So you use the distance between a coordinate and origin to demonstrate both the magnitude as well as the direction of the vector. So one example is this a, which we can say, let's just say it's x hat plus square root of 3 y hat. So what that means is we have, in this case, when it's two dimensions, we have our x direction and y direction. These are unit vectors. So x hat is a length of 1 in the x direction. Y hat is a length of 1 in the y direction. So you will have, if it's 1 x hat, then that means you have length 1 in this direction. Root 3 y hat means that you have root 3 in the y direction. So root 3 y hat would just be a vector that's root 3 long going up this way. X hat will be a length of 1 vector going this direction. And when you add these two vectors together, we'll talk about vector addition later, but what you end up with is this point here, which is at 1 comma root 3, and it will have a length of, according to Pythagorean's theorem, it'll have a length of 2. So what you are trying to express is in this case, I think force is often the most intuitive quantity to talk about this, but you are saying that there is a force in this direction, so in this case 60 degrees off the x-axis, and the length of this arrow is 2. And remember, this is a magnitude and a direction. It doesn't have a location. So this is just a force. And it can really sit anywhere, right? But you're using, by convention, you're indicating the direction and magnitude by identifying a location in this space and taking the distance between the relative relationship between that location and the origin to indicate this magnitude and direction. Once you understand what a vector is, a scalar is just a vector with less information. In this case, a scalar only has magnitude information, so no direction involved. One example would be the meaning of life, the universe, and everything, right? So we'll just say everything is equal to 42, right? So that is a scalar because there's no unit vectors involved, which means there's no direction. It's just a quantity. So let's think about another way to drive this home is let's think about actual examples between a vector and a scalar. So an example of, like we talked about, force would be a straightforward one where it has both a magnitude and a direction. You can also see velocity is one, because you can't just say, if you say, remember the difference between speed and velocity. Speed is just saying I'm going 60 miles an hour or 20 kilometers an hour. Velocity also has a direction associated with it. So you have to say, for it to be velocity, you would say it's 20 kilometers an hour due east, right? Scalar, basically anything that doesn't have a direction associated with it, but is still a quantity. So an example would be mass, the meaning of life, as I mentioned before, but also, you can also think, other things like the amount of money in my wallet, right? that is a quantity. It doesn't really have a direction associated with it. So once we have these two established, let's talk about scalar fields and vector fields. So by field, what that means is that you have basically it means you have a function, and whether it's a scalar or vector, it's defined by what comes out of it. So with a vector field, we will usually use a capital letter, and we'll have a vector notation on top of it. But what a vector field is it tells you it's a function that converts a location into a vector. So you have x, y, z, you have a location that goes into the function, and then what comes out is a vector. So f of, we'll say this is x1, y1, z1, then what comes out is capital F of x1, y1, z1, and it will take this form here because it's a vector. And so an example would be, and this is kind of where force fields come along, and all the Star Wars, all the intuition you build watching Star Wars and considering issues like the force and midichlorians come in slightly handy here. So let's just say an example of a vector field is, in this case, 2x x hat plus y y hat. So what that means is that if I plug in a location, in this case, all the locations in Z will have the same value. But if I plug in, since it's independent of Z, since there's no Z in here, but if I plug in, say, what's the field that a particle will experience at, say, x equals 1 and y equals 10, then you just plug that in here, and this expression, if this expression describes the field of forces, you'll plug that in, and you'll see that at that location the force would be 2x hat plus 10y hat. And you would often describe this, you can visually describe this as you can draw the space, and then you can add arrows on it. And these arrows, remember, we define a vector as a relative difference between this and the origin. You would draw out that arrow of where it is at that location, and then shift it so that it's at that location, at the location of interest. So in this case, the vector gets longer as x and y get larger, and so you see these arrows just kind of get larger and larger as you move away from the origin. But to find the point, the value of the vector over here, what you do is say it looks like this. So you draw it out over here, you calculate it looks like that, and then you calculate at the origin, and then you shift it to the location. And so again, the basic characteristic is that there's it's a function. Location goes in the case of both of these, but what comes out is a vector. And so you can imagine what a scalar field is in contrast, right? It's also a function. We denote this by not having a vector line on top and also making it lowercase. And the only difference with a vector field, you still put in a location, x1, y1, z1. So location goes in, but then out come scalar values. So we'll also refer to this f of x1, y1, z1. And so a function, say if you had, in the case of a vector field, one example would be if this expression described the amount of force that you would feel at any given location, you can plug in locations and then calculate how much force there is. Scalar field, you can also do something like mass, right? If you have a function that describes the weight of an unfair die at different locations, you might have some kind of function where you plug in the location, it'll tell you how much it weighs if the weight is not uniform across a device or across a volume of interest. And so, an example of that following this, I'm primarily doing this here to show you the notation, would be f of xy is equal to 2x plus y. So what comes out is a scalar because there are no unit vectors. And then when you plug in values for x and y, you just get a number. And so again, we denote this with lowercase. We don't have a hat on top. And And then same thing at the output. So because there's no x hats and y hats, no basis vectors or unit vectors in the expression, you also don't get unit vectors at the output, and so you get a scalar. So just keep these in mind. These are all different quantities and they are not interchangeable, and don't get them mixed up. So note the notation, note what they are, and build your intuition from there.